this is Varun Dutt from IT Mandi. We are continuing in the Large Applications Practicum course. This is the last module in the course on software reverse engineering. So I'm going to tell you about what is software reverse engineering, why we want to do software reverse engineering, and what are the benefits of software reverse engineering. So let's get started. So software reverse engineering is opening up the program's box and looking inside. It's like opening up the executable file to see how it works. No screwdriver is needed. It is purely virtual process on the computer, unlike other types of software engineerings or reverse engineerings where a screwdriver may be needed. The process is used by a variety of different people for a variety of different purposes, prevalent in the industry to outpace competitors. So the idea is that if you have an executable file and you want to understand how it works, you need to be able to reverse engineer it to be able to find out how it works. Software reverse engineering allows us to reverse engineer a executable file to understand its working, so be able to understand how it works. So software reverse engineering applications include, of course, malicious software. So if some software can be broken or cracked, one can use software reverse engineering to understand how one can develop cracks for a software so as to prevent tampering of the software. We can also use software reverse engineering to find encryption and decryption algorithms, and particularly the efficacy of such algorithms. Okay, and one other thing which is important is that software reverse engineering can also be used to find cracks and copyright infringements for copyright software, music and movies. So if any software, if it can be reverse engineered, then we need to be wary about that people may be able to develop, use these loopholes in the software to be able to copyright infringement. So we can catch this using software reverse engineering. So software reverse engineering, of course, has been used in the industries for developing competing software. Also, as I told you, evaluating the software quality and its robustness. Now, software reverse engineering is done through tools, and there are at least 3 types of tools which are prevalent in the real world. One is called the decompiler, which is basically allows us to go from executable file and exe file to the source code. And such kind of decompilers include the SoThing decompiler, JAT for Java, .pete for .NET, and generally this is done for a managed software process. Managed software process is one where the software created, the executable file created, is independent of the underlying hardware, and there are things like bytecodes created which can then be compiled in real time to get the executable file. However, in case software is not managed and its executable is hardware dependent, then in those cases, like for example C++, then in those cases we may not be able to do decompilation. And the best possible may be disassembly. So disassemblers are going from the executable to the assembly level code, which is one level up from the process. And disassemblers like OllyDbg as well as IDEA Pro, Softies exist, which allows us to open the executable file and to be able to access the assembly level code. We also have debuggers, which allows us to observe the assembly level code while it is running on the CPU, and generally OllyDbg or disassembler tools also have debuggers built into it. So before we understand the process of disassemblers, debuggers, we need to understand a little bit about the Intel architecture, at least the architecture of the microprocessor which is running on the computer. So generally, we may understand that there are memory structures called CPU registers which exist inside the CPU, and these CPU registers are fast memory located in the CPU itself. They are basically used for low-level operation, and they are super fast data storage for processor. It is on the processor, and for x86 architecture, they are usually 8, 32-bit long registers, as you can see EAX, EBX, ECX, EDX, ESI, EDI, and ESP, which is stack pointer, and the base pointer. Two of these, which are these two last two, hold base pointer and stack pointer that can be used for navigation between the instructions as well as for subroutine calls. The registers are even faster than the static RAMs which exist, also known as cache, and of course the dynamic RAMs. So here, the general purpose registers, as you can see, the EAX register has a 32-bit register in a 32-bit architecture, and it has the AL lower 8 bits, AH higher 8 bits, AX the lower 16 bits, and EAX, which refers to the entire 32 bits. And then these are general purpose registers used by the microprocessor, and then stack pointer and base pointer are used for subroutine calls as well as movement between instructions in the code. So in general, we know that there is something called assembly language, which is what the high level language like Java, Python, C++, when we write programs in English language, they get converted into assembly level language and further into the machine code, which is consisting of zeros and ones. So assembly level language is unstructured and is based on very primitive instructions, which are divided in the following general types. So these instructions may be move, used to copy data from one cell to another cell, between registers, and between a register and a cell and memory. And also there are instructions like push and pop, which operate on memory supported stacks. And then there may be instructions like add, sub, increment, which cause arithmetic operations and can operate on with constants, registers, also memory cells. And then there are control flow instructions like GMP, jump to label in a cell in the memory, JD, jump if condition is met. Conditions are generally mentioned one step before this instruction. Jump equal, jump when equal, jump not when not equal, jump when last result was 0, GJZ, GJG, jump when greater than, JGE, jump when greater than or equal to, JL, jump when less than, JLE, jump when less than or equal to, CMP, which is comparing the values of the two specified operands, call and return, which are to implement, which allow us to implement subroutine calls and return statements. And generally, the control flow instructions are where decision making happens in the code, and these are of interesting value because these are where we can recognize them in the assembly level code and be able to update them or be able to execute them to be able to understand how the code works. So next slide, we have this particular link in which if you want to learn more about assembly level code, you can go here and you can learn about it. But the kind of assembly level knowledge I have given you is more than sufficient to be able to understand the code, which I will be showing you in a short bit. So here we wanted to show you an unmanaged compilation process, which is typically the process which is done in a C++ program. So as you know that a C++ program may consist of C, CPP files or .h files, and these files are converted, goes through a set of steps like preprocessing, compilation, assembly, which is giving .o files or object files, and finally linking, which is creating the executable file. So the idea is that these steps are hardware dependent, also microprocessor dependent and OS dependent, and therefore when we get an executable file, it is an unmanaged process and we can only go to the assembly level code from the executable one level up. So this kind of code we can actually run through tools like OllyDBG or DGP, which are disassemblers, also built-in debuggers. The other is the managed compilation process, which is generally followed in .NET programs, Java programs, Python programs like C#, VB.NET and other .NET languages, where when you compile these programs, you get something called the Microsoft Intermediate Language Code or the bytecode. And then when we actually execute the file, the just-in-time compiler will actually create the native code or the executable file to run it. And therefore, because the bytecode is hardware independent, we can go back from the bytecode to the source code, and therefore we have something called the decompilation process. So moving ahead, in this tutorial, I'm going to show you how we can use only DGB to be able to open up a C++ program and to be able to disassemble that program and then be able to reassemble that program as need be. And then we are also going to look at other managed compilation processes in the next lecture. So the activity in this lecture is to first download OLEDBG and then set it up. And then we want to open an executable.exe file which has been already pre-compiled, which accepts this code 82634 and rejects other code. So we want to disassemble it and try to change the code in such a manner that this code or any other code can be accepted by the software, so that we can disassemble and learn about how to reassemble the 4 after disassembly. So please try it out at your own pace, and then we can discuss in the next lecture. Thank you.